when it comes to two-dimensional motion, the first thing we're going to cover is projectiles. That's what we're going to be talking about today. And after projectiles, we will do a little bit of trig work. That's going to be tomorrow. And then we're going to do vector addition. So I want to start by defining projectiles for you, at least in the context of what we're going to do with projectiles. A projectile is any object that moves in two dimensions but experiences an acceleration in only one. I'll say that one or two more times, but a projectile is any object that moves in two dimensions but experiences an acceleration in only one. So imagine a guy standing on top of some platform and he throws the ball sideways off the top of the platform. Now, it's one of those problems where I think we can all kind of agree on a few things. First, if I want to kind of establish some way to communicate this to other people, I've got options, but I'm thinking if I got to choose a direction for X and Y, probably that's not ideal. Would you agree? That in establishing what direction is going to be X and what direction is going to be Y, I think my problem helps dictate that just a little bit, don't you? So I think it probably appropriate that we can choose an up and down direction to be one of those and a sideways direction to be the other. All that I need you to recognize is that these two directions, X and Y, do have to be perpendicular to each other. It's kind of required for it to be considered an XY coordinate system. So I'm going to start every problem that's like this by picking a place somewhere in the problem and establishing the positive X and positive Y direction. So I'm going to go with positive X here and positive Y there. Seems to make the most sense to me. Now by doing this, I've also kind of established something else. I've established that the ball is being thrown in a purely horizontal manner, meaning the ball at time zero is experiencing a horizontal velocity, or has been given a horizontal velocity. The kid threw the ball off the roof in a horizontal direction. We are aware from our prior work that there's an acceleration due to gravity that will be straight downwards. Now, I think most of you understand what's going to happen here. That the ball's going to fall towards the ground while moving sideways. It'll have a path something like that. Won't you agree? Does that make sense? Does this ball follow the definition of what we think a projectile will be? Is this thing moving in two dimensions and experiencing an acceleration in only one? I think we're good, right? The acceleration is purely in the Y direction. We have no acceleration in the X direction. We'll have to do some things like ignore air resistance to make that really true. Now, what this suggests is that at time zero, the object's Y velocity is zero. We throw it perfectly horizontal, it has no Y velocity. I'm probably going to have to put a little naught there to tell me that this is the Y velocity for sure, but the initial Y velocity, the velocity that it starts with in the Y direction. I think that's important because after a few moments, the ball's going to be here. Now, there's an acceleration in only one dimension, which suggests that the horizontal velocity will not have changed. However, it experienced an acceleration downwards. So I think we can all probably agree that it now has some kind of y velocity. Right? It acted on by gravity, accelerated at 10 meters per second squared downwards. Now, the horizontal velocity hasn't changed. That component of the velocity stays the same. This word, component. I'm going to need you to define this word, component. The ball has two velocities at any one moment. It has a horizontal velocity and a vertical velocity. But the truth is, it only has one velocity. It's moving that way, right? We just know that that velocity suggests it's moving a little bit horizontally and a little bit vertically at the same time. The amount that is moving horizontally, we say, is the horizontal component of the velocity. And the amount that it's moving vertically would be the vertical component of the velocity. Component vectors tell us how much of a vector is in each of our directions. Component vectors tell us how much of our vector is in a given direction. So I could say x component or horizontal component, I'm referring to the same thing. But component vectors tell us how much of a vector is in a given direction. Now, I hope you recognize that component vectors probably are going to be related to trig. Can you kind of see that in your future? I mean, it should be kind of clear even right now that if I wanted to know what the total velocity is, I'm probably looking at Pythagorean theorem or something like the Pythagorean theorem to get there. Can you see that far in advance? If you can't, you're going to have to learn. Because I'm also imagining that after a few more moments, the object almost makes it to the ground. At this time, the horizontal velocity has not changed at all. It's a constant. It's only accelerating in one dimension, so its horizontal component stays the same the whole time. I've tried to make sure the arrows were the same size the whole time. But the vertical component has been continuously accelerated and is changing. So the ball is getting faster all the time, but one component of its motion is staying the same while the other component is increasing. Are we good so far? Now, if you're really paying attention, you understand that we're probably going to have a displacement here, how far the ball fell downwards. And we're also going to have a displacement here, how far the ball fell to the side. Projectile problems require that we consider where the object might land given the circumstances of the object's flight. So I would encourage you to consider how might you organize yourself best to try and figure out how to deal with problems like this. For example, let's say that the guy is standing on a 10-meter tall rooftop. He throws the ball sideways at 5 meters per second. And we're interested in figuring out where the ball lands on the ground. The object is experiencing an acceleration in the y dimension. So let's talk about the vertical dimension. The ball is experiencing an acceleration in the y dimension, then the ball has the properties of an object in uniform accelerated motion. Right? The 5 motion variables, but I'm writing them a little bit different to isolate them, to make us understand that we're dealing with the vertical component. So not delta x, but delta y. Not v naught, vy naught, the initial velocity in the y dimension. Not just v, but vy to indicate the final velocity in the y dimension. All of these kind of written so that we have an idea that this is just the vertical part. At the same time, we have a horizontal part. There's clearly going to be a horizontal displacement. In physics parlance, we call this the range. There's no acceleration horizontally, so whatever the initial velocity is horizontally, that's also the final velocity. So we can just list that as Vx, because it doesn't change. And then there's, of course, how long it takes to move sideways. The thing about all projectile problems is all projectile problems are linked together by the time. The time it takes the object to fall is the same as the time it takes the object to move sideways. So in all these problems, we're linking together time. We're finding the time on one side and using it in the other. In fact, this has all the tenets of a uniform accelerated motion problem, where I will have to find 3 pieces of information in order to get the time. While the horizontal side, there's only 3 pieces total there. There's no acceleration, so range equals Vx times t. This side, though, subject to all the motion equations. It'll depend on what we're given. So let's consider this problem specifically. The object fell a distance 10 meters. Delta y, 10 meters. The object's experiencing the acceleration due to gravity, 10 meters per second squared. The object was thrown at 5 meters per second. Well, there's 3 different places to put a velocity. You'll have to be careful about that. Because although I clearly am telling you where to place it here, in your problem, you need to read carefully to note where that velocity might go, or if you have to do something to it first. I think for the time being, this problem is pretty straightforward. I'm telling you it's the horizontal velocity. The object was thrown horizontally at 5 meters per second. In fact, I go in further and say because it was thrown horizontally at 5 meters per second, its initial y velocity was 0. So just like our other problems, you need to identify the information that's been provided in the problem. And from there, use it to kind of fill out the information given. Projectile problems are a simplification. Because the acceleration is only 1 dimension, we can separate the problem and work one side at a time. They're not connected directly together. So we can work just with the vertical side or just with the horizontal side. That's what makes them a simplification. Real problems like hitting a golf ball, that wouldn't work here because they experience an acceleration in multiple dimensions at once. So we're dealing with a pretty straightforward simplification. Even a football wouldn't obey this. Football is shaped so that it has lift. So if you throw it in a spiral, it behaves differently than if you kick it and it tumbles. So any kind of ball thrown in real space, the air affects its motion. If you remove the air from the system, they'll all act like a standard projectile. Now, we still have to apply direction to our problem. You don't want to stop that. That step is important. And since I established at the beginning that upwards is positive, then it fell downwards 10 meters, and the acceleration is pulling it downwards 10 meters per second squared. I have to be consistent with my application of direction. However, from this point forwards, I just have a motion problem. I can handle the motion problem. I need to figure out the time. How long does it take the ball to reach the ground? So I'll probably choose a motion equation. I don't feel like I need to write them all out ahead of time like I used to. I think we can skip ahead a little bit. And I don't know that I have to convince you that, delta x becomes delta y in these functions and all that. We're all okay with that, right? You have your little note card with the motion equations on it. I'd use it. Just understand displacement is displacement. Square root of 2 seconds. That means this is 1.4, this is 1.4. When you find the time applies to both. It moves up and down in the same amount of time that it takes to move sideways. That's the whole point of a projectile problem, is you're trying to find the time so you can use it in both places. Once I have figured out how long it takes the ball to fall to the ground, then I can use it to figure out how far sideways it's moved. Pretty straightforward. We good so far? There's other questions. There's other things we could do. I mean, I could ask you how fast the ball is going when it reaches the ground. That might require that you figure out this component and then use a little bit of trig to figure out the total speed. I don't think that's asking too much, but we'll cover triangle stuff tomorrow to make this part a little bit easier. And the problem can be phrased different too. Like, what if instead of telling you how fast it was thrown, I want to land in a bucket that is 10 meters away? So if the bucket is over here, it doesn't change the problem very much, does it? If I want to land in a bucket that's 10 meters away, well, I need to find out how fast I go sideways. Is that going to change how long it takes it to reach the ground? No, because how long it takes to reach the ground depended on how tall the building was and whether it was thrown upwards or downwards. If that doesn't change, then the amount of time it takes to fall doesn't depend on how fast you throw it sideways. So if I throw it sideways at 5 meters per second, it will take the same amount of time to reach the ground as if I throw it sideways at 10 meters per second. How long it takes to reach the ground just depends on the vertical portion. So that's what controls how long it's in the air. These are standard projectile problems. In fact, this one that we just did here is what I like to call a type 1 problem. I call it type 1 because it has a simplification. In a type 1 problem, the initial y velocity is 0. Anytime you can introduce a 0 into your problem, it simplifies it. We're not going to stay with these very long, but in your homework, you'll notice I broke the problems down by type 1 and type 2, and I don't think there's any type 3 in your homework. And in them, I even broke them down into other subsets. Problems where you're given this velocity and asked to figure out where it lands, ones where you've been given where it lands and asked to figure out what the velocity is. I've given several different versions of them. All the answers are there too, so practice. I want you to be proficient. There are type 1s and other types of problems, and this is where tomorrow's going to come in. I mean, I think clearly there's going to be an opportunity for us to kick something at an angle. All right, just kicking a football. Ball leaves the ground at an angle. That means the object is going to have both a horizontal velocity and some initial vertical velocity. That's going to change the nature of what we have to do, right? We're going to have to figure out how much of the velocity is in the x direction and how much of that velocity is in the y direction. That's going to be the trig. We need that because the problem is still going to be solved the same way, by finding out how long it's in the air for, and that's going to be dictated by the y velocity. This problem is not so terrible because generally, in a problem like this, we're expecting it to come up, back down, landing at the same height that it took off at. These problems are characterized by having a delta y that is 0. Again, anytime you can introduce a 0 into the problem, you make your problem easier. And I call these a type 2 problem. They introduce a 0. The y displacement is 0. So whenever you launch an object from level ground and it lands back on level ground, again, it introduces a 0. Now, in order to do this problem, we're going to have to handle the trig. So that's what we're going to be dealing with tomorrow. So I want you to bring your A game for trig. Because with a B on the next test, 2s are fines. That'll be good. If you want an A, you're going to have to do the big daddy. Eventually, we've got to get to this style problem. And this is the whole package. You take the football on top of that roof, launch it at an angle. This one's tough. The math is hard on this one. You can't introduce any zeros into the problem. So it has an initial y velocity. And if you're paying real attention, you realize that that's going to make your math harder because you're going to have a quadratic that you have to solve for the time. And for some of you, that's tough. And that's going to make doing this part harder too. So there are levels of how difficult these problems can be. I call this a type 3 because it's the most difficult. We're going to focus on type 1 and type 2 in this class, but I want you to be understanding that if you want an A on the next test, you will have to be able to do a type 3 problem. If you're I think it's time for you guys to show that you've been listening. So let's try this, see if you guys can work this one out. We're going to do something relatively easy, so you've been paying attention. I'm going to roll a little ball off the top of a building so it leaves the building with some horizontal speed. The building's 25 meters tall, but I want that ball to roll right into a bucket that's located 10 meters away from the edge of the building. So the ball's going to go right into the bucket. How fast do I have to roll it for this to happen? Practice, the answer is 4.5 meters per second. See if that's what you get. All right. So I'm going to use things that are not a part of your math class on purpose because I don't want you to be trained by what you've been trained in your math class. I'm going to use something, though, that you are, I hope, somewhat familiar with. Okay? So you're familiar with north and east. I'm trying to break away intentionally from talking about X and Y and deal with something different. That way you don't attach this directly to some of the staples that are in your math class. Because your math class has trained you in sometimes detrimental ways for what we do in this class. Raise your hand if you've ever done unit circle work yet. Okay? So the problem with unit circles, everything is always measured from X being 0. And that's not the way this class works. So we're going to break away from that a little bit. Besides, on a compass, north is 0. And on a compass, the angles go clockwise. In your math class, east would be 0, and the angles go counterclockwise. You understand that it's just not the same, but it's still the same math. So let's talk about the original idea here, that I am going to walk directly towards a student in a room. And based on where the walls were, this would be 55 degrees. And let's say I was going to walk 12 paces or 12 meters. Now, in my room, can't do that, right? Can't walk across the desks. But let's say that this teaching thing wasn't in the way, so let's say I could go this way first, and then this way. That would be a way to get there. Of course, I could also go this way first, and then this way. This would also get me there. You understand that the order in which I decide to go doesn't matter. Do you see that that's true? What I mean by that is this direction and this direction will still be the same length. And this direction and this direction will still be the same length. You guys follow along with that okay? So the first thing you have to do is establish a triangle that you're going to use to break your problem up into 2 dimensions. This is different than how you'd be taught this in your math class. So listen closely. We, the person solving the problem, gets to decide where 0 is and how the angle is measured. We pick the x-axis. We pick north, south, east, and west. We choose that. When we're breaking our problem up into 2-dimensional problems, into 2 one-dimensional problems, we choose the coordinate system. Now, once we've chosen the coordinate system, we choose the triangle we wish to use to solve the problem. Neither one of these triangles is better or worse than the other. However, I gave you 55 degrees. To use it, you have to use the yellow triangle. If you decide to use the green triangle, what will this have to be? They are complementary angles. I use the word complementary in here all the time. Complementary angles add up to 90. If you don't know that, put it on your trig cheat sheet. Supplementary angles add up to 180. I use that word too. It's supposed to be part of your vocabulary. If it's not, make it part of your vocabulary. Complementary angles add up to 90. Supplementary angles add up to be 180. I also use vertex, corresponding, alternate interior. All those things you learned in geometry we use in here. I'm going to use the yellow triangle, arbitrarily choosing it. I don't have to, I'm just going to. You could use any of these for what we're about to do. So, if you're writing this down as a series of steps, step 1, pick your triangle. And I don't say that arbitrarily. I say that is always your first step. How are you going to break your problem up? What's your one-dimensional problem going to be? Now, once you have done that, some of this vocabulary is made up just for this purpose, but you'll understand why you need it. There are three angles in this triangle. You need to choose the angle of focus. The biggest problem I see with students is not understanding that trig is based on one of the angles in the triangle, and you have to know which one. So you are choosing the angle of focus. That's step 1. Once you have chosen the angle of focus, label your sides. You know the labels. Opposite, that's the one across from the angle. Adjacent, the one next to the angle. And hypotenuse, the longest side of the triangle. It is the one that's across from the right angle. Understand something, the hypotenuse is always the longest side. When you're done with your math, make sure your math agrees with you, because I looked at some of your math when we did this a couple days ago, and I gave you a triangle to see if you could solve it. And many of you had other sides longer than your hypotenuse. So check your math. Now, you're supposed to be aware of something, and I don't know that you are. There's a mnemonic. You've heard the mnemonic before, right? If you've never heard this mnemonic, it's just SOHCAHTOA. It used to be Mr. SOHCAHTOA, Professor SOHCAHTOA, and back when I went to school, culturally insensitive, Chief SOHCAHTOA. So SOHCAHTOA has been around since I was a small person, smaller than this at least. So yeah, SOHCAHTOA. It is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So step 2, write out your trig functions. I know the way I'm doing this is laborious, but if you're not good at it, you need to be. So when I say write out your trig functions, I mean write out what the functions are. Okay? Now, it's at this moment where our set of steps has a fork, and we're going to do both sides of the fork. We're going to do both paths. We can only do one path at a time, though. So you have to ask yourself a question. Were you given an angle and a side, or were you given 2 sides? That's the only way these problems come. So it's either an angle and a side or 2 sides. This problem gave us an angle and a side. So we're going to do the path where you have an angle and a side. In a few minutes, we'll come back and do the path where we have 2 sides. Got it? So right now in your set of steps, choose which one of these do you have? A side and angle, or do you have 2 sides? We have an angle. So I'm going to write the angle in. From here, the series of steps is a little different, or is, you don't know what series of steps are. From here, what you're to do is write in all of your known quantities that are left, which will just be the one side. It's going to be written in 2 places, because you'll notice with all these trig functions, it shows up twice. All the possible permutations are there. So we have the hypotenuse, so I'm writing it in where the hypotenuse goes. Now, using your calculator, check to see that it's in degrees. This is where you have to check. This is the point in the process. Whenever you're going to hit the sine, cosine, or tangent button, you have to check first if your calculator's in degrees. So put this right in your trig cheat sheet because you'll forget, especially later in the year when you come here from your math class and you just had it in radians. Compute all 3 trig functions and write it down to 4 places. So we're going to do sine of 55, cosine of 55, tangent of 55. Now, every calculator does this different. Probably if you're using a TI, you're hitting sine, then putting in the angle, and then hitting evaluate or equals or whatever that button is nowadays. For old school, you're putting in the angle first and then hitting the function. You should be using the calculator you will use on the AP exam and not your phone. All right. You want to get this right, correct? You want to do this without mistakes, correct? At this instant, if there's a negative sign, you're in radians, okay? So I put that in there on purpose to make sure you check, but if you have a negative sign now, you're in radians. All of our angles are going to be less than 90. They should always give you positive values. The only way you would get a negative sign here is because your calculator thinks you're giving it a bigger angle than it is. Now, from this point, there should be an obvious path to get the unknown side lengths. You have to find which functions will do that. But there should be an obvious path to get the unknown side lengths. So from here, you should be able to compute the unknown side lengths pretty easily. So I'm going to do that. My opposite side is 12 times 0.8192. My adjacent side, 12 times 0.5736. But wait, there's more. Here's how I want you to know that if you're getting these wrong, it's because you want to get them wrong. Because you can check your work. You can make sure your sides are right and that they match what you expect. Because first, you could do the Pythagorean theorem to see if this works out. You could take your 2 sides, square them, add them together, and then take the square root and see if it equals 12. Something that's completely separate from trig that allows you to check your work. If you've screwed this up, you'll know right then that you've made a mistake. You can also take the opposite side and divide by the adjacent side. It should be 1.4281. There's less value in doing that because if you did the trig wrong, you probably did that wrong too. But the Pythagorean theorem will check your work for you. So if you get it wrong again, that's on you because you chose to. You have a means to check your work. Now we've reached the end. That's what this process will do. We had a fork in the road, so we're going to have to explore that. But at the end of any of these problems, no matter what, the trig was intended with a purpose. And it tends to get muddied because the purpose gets forgotten. Remember what we were trying to do. We were trying to find a way to reach this point in the room, right here. We were given one way, but we couldn't do it because the desks were in the way. We have another one. It says to walk along the X direction, the east wall, 6.88 meters. Then turn 90 degrees and walk north, 9.83 meters. Remember, these were side lengths. They represented distances. Don't lose sight of what your problem was about. It's easy to do because you get bogged down in all the trig. And give yourself room, right? Give yourself room to do these problems. You'll need it. All right, we got to address 2 instances and the other problem. So let's address the other fork. going to use the same kind of stuff. I'm not changing it very much because I don't really want to throw too much new at you. Let's say instead you're given this. You have to walk 25 paces in the north direction and then turn and walk 60 paces in the east direction. I would like you to tell me, of course, what is the direct distance to get there and what angle would it take? This is the other version of the problem. This is the other fork in the road. Now, before we even start, there's one difference here. I said to you before, you can choose your triangle, and I stand by that. We could choose a different triangle. But if you choose a different triangle, if you choose to use this triangle, but you were asked to find this angle, do you realize the green triangle can help you find that angle? But you need to be careful about what you choose to do here. So although either triangle will solve the problem, I would encourage you, if you're asked to find an angle, you use the implied triangle that's given. Does everybody understand what I'm trying to say here? If you're asked to find an angle, you want to make sure you give them back what they want, not the complementary angle. So I would encourage you to use the implied angle. Steps don't change. Choose your angle of focus, we have. Identify the names of the sides. So, opposite, adjacent, hypotenuse. Write out your trig functions. Fill in what's been given. Okay, this brings us right to the same step, right? I did it quickly, but not impossible. This is the fork in the road. This is where you have to ask yourself, were you given an angle and a side, or were you given two sides? In this case, this is the process we were given two sides. If you're given two sides, your angle is unknown. But what it means is one of your ratios will be complete. You don't know which one's going to be the ratio that's complete, but one of them will be complete. In the case of this problem, it was a tangent function that was complete. So in order for you to do this problem, you're going to be working in reverse. We want to find the angle that produces this particular ratio. So compute the ratio first. So it's 60 divided by 25. I got 2.4. We would like the other ratios. Now listen to me very closely. I told you that I'm trying to train you on how to do trig. I know that you guys have a method to figure out the hypotenuse. What I'm about to tell you is that we're going to do the whole problem with trig. I know you can find the hypotenuse another way. It's an excellent way to check your work. But the whole problem can be done with trig. I want to show you that it can. So we need to figure out the angle from the ratio. This means having the process done in reverse. We are going to use the anti-trig function, or the inverse trig function. Now be careful here. This is also the part in your steps where you check to make sure your calculator is in degrees and not radians, because you want to make sure it gives you back a value in degrees. But it's the same thing. It's just that you have to hit the second button and then your function, generally. I got 67.38 degrees. Is that what you got? I hope so. Now, a couple things to note. If the ratio is more than 1, it's got to be an angle more than 45 because we're dealing with tangent, right? So that's the only one that's an easy one to know because tan of 45 is 1. But these are little things to try and help you out. Now, I'm going to go back in here and write in that I know what the angle is. It's 67.38. And I'm going to compute all the ratios. I'm going to find the cosine of 67.38. 0.3846. And I'm going to find the sine. 0.9231. I'm back on my set of steps. My set of steps was to find all 3 ratios. I have found all 3 ratios. Once you've done that, there should be a pathway to find your missing sine. To find your missing side. I see a pathway to find my missing side. However, 7 of you can't find the missing side. I looked at your pretest. You do this wrong. Meaning you have a hard time finding for a variable that's in the denominator of a fraction. I don't know who you are specifically. I just did a rough count on the number of people who couldn't do it in this class. It was 7 in this class and 4 in the first period. So if you don't know how to find h, or you did it wrong, let's be very clear. H has to be bigger than 60. Do you see why that has to be true? Because I have a fraction, and 60 divided by this number gives me a number less than 1. But a lot of you on your pretest got a number that wouldn't work. So let's recognize that you multiply both sides by h. And then divide both sides by 0.9231. I got 65. Now, check your work. 25 divided by 65 had better be 0.3846. Or do Pythagorean theorem to check your work. But check your work. You have 2 different things you can do to check your work. We good? Yep. What kind of calculator do you have? Okay. So tangent of an unknown angle equals 2.4. What I'm really doing is I'm doing the inverse tangent of both sides. That's right. Arctan or arc angle. So does that clarify it? Yeah. Okay. All right, folks. Let's put it into practice. Just done in these applied. The whole thing was we had purpose for this. I want to see if you can put this into practice with our purpose, why we're using this in class. I would like to talk to you about the possibility of a projectile where the projectile is launched at an angle. We know from our discussion yesterday that with projectiles, by the way, this is not part of your cheat sheet anymore. With projectiles, we need to break our problem up into a horizontal problem and a vertical problem. Right? So if I tell you that an object is launched at 20 meters per second at an angle of 35 degrees, you would have to find how fast the object is launched horizontally from that and how fast the object is launched vertically from that. Right? So, can you do that? can you find what Vx and Vy naught is? Your trig cheat sheet should help you. Okay? You want to assemble a triangle from the information provided, and then use that triangle to find the one-dimensional parts of the velocity. This should work the same way as what we just did. You have a trig cheat sheet, that should help you. I want to come by and see what it is that you find for Vy initial and Vx. A cursory walk around the room shows me I have about half a dozen people who are just staring at their paper, like they don't know what to do. Let me direct those people real quick. Remember, we're trying to take this circumstance here. We need two one-dimensional problems. So you needed to create a triangle. I think the appropriate triangle is probably that one. That would probably work because of the angle that was given. So I'm assembling this triangle, and that's going to make this the opposite side, this the adjacent side, and this the hypotenuse. You have to do this. Remember, this is just step one of the problem. The problem has nothing to do with this. This part has to be transparent. Now, because there's more struggle bus in this room than first period, I'm just going to talk out loud as I work the problem. Many of you are done, I understand that. Let's see, sine is opposite over hypotenuse. I'm not going to write O over H. I can look at the triangle and see what it's labeled and write in its labels. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. I was given the angle of 35 degrees. That means I can take the fork in the road, which allows me to find the trig ratios right away. So I'm going to find the trig ratios. I don't need the tangent ratio, and I didn't leave myself very much room to write it in, but I can find the sine and cosine ratio. Found my two ratios. Once I have my ratios, I see a pathway to solve for the y velocity. So if I were you, I might keep more decimal places. Well, that doesn't equal that. And I can find my horizontal velocity. Now, truth is, this is the 16.4. This is the 11.5. Okay. Now, the trig was just necessary to get the problem started. Which one of these numbers stays the same? 11.5 or 16.4? I want to hear everybody. 16.4, that's the horizontal one. It stays the same. Remember, there's a whole other problem that has to be done now. Something that's not about trig. The trig is just transparent. I need it to do the problem. Problem's going to be launched from the ground. If it lands on the ground, then delta y is 0. I don't know the final velocity, but the acceleration is likely 10 meters per second squared. And I'm interested in finding how long it's in the air. If I know how long it's in the air, I can tell you where on the ground it's going to land. And still, projectiles is still our study point. Now I'm going to choose upwards and to the right to be my positive directions. That'll make this launch velocity positive. It'll make the acceleration negative. And it'll make my horizontal velocity positive. I'm going to use a relationship that'll help me find time. I'm thinking 0 equals 1/2 a t squared plus vy naught times t. I chose one of our motion equations that has all the stuff in it except for final velocity. I can factor out one of the t's, set it equal to 0. That is one of the times when the object is on the ground. The second time will tell me when it's on the ground again. So that looks to be negative 5t plus 11.4 equals 0. So t equals 11.4 divided by 5, or 2.28 seconds. For all you in the back trying to see, that's what I did. Now, I want to find the range, so this is 2.28 seconds, and this is 2.28 seconds. Remember, it goes in both places. Using my chart, range equals 16.4 times 2.28. I find that it lands 37.4 meters away. That's where along the ground it strikes the ground. Do you understand now why we have to do the trig first? Yes, ma'am? Yeah, I mean, all the information given to us was only presented in 2 significant figures. So, I mean, adding a significant figure is not a problem. You don't need to give me more than that. What I would want you to do, most of our stuff isn't numerical. And if it is, it's multiple choice, so they're going to truncate down anyways. When we're doing numerical work, keep lots of decimal places in your calculator, but your final answer should be, try to adhere as much as you can to significant places, or just give me one extra place besides that. Okay? Yes, sir?
Can we assume that Vy is going to be 0? Final velocity?
I don't think Vy will be 0. We can try it. We can figure out what Vy is right now. Vy equals negative 10t plus Vy naught, which would be 11.5. Right? I'm not doing this to exploit anything. I think it's going to be moving downwards when it hits the ground. In fact, I think our answer for Vy is going to be negative 11.5, or really close to it. And that's because I think it's going to be going downwards the same speed it went upwards, because we're landing at the same height. Does that make sense to all of you? Now, something to keep in mind as you're packing up, in answer to David's question, you could be asked, what is the maximum height of the projectile? And that would be when Vy is 0. That's a different style of problem. We haven't seen that kind yet. All right.